I'm going to show you a little trick with credit card numbers. So I bet most of you have a credit card. You probably shouldn't, but you probably do. So if you do, I want you to go ahead and pull it out of your pocket or go grab it. I'm going to show you something we're going to do with the numbers. So I brought my credit card. This is a credit card I have. Now you'll notice I have strategically covered up some of the numbers because I don't want to be buying graphing calculators and clothes and who knows what else for all of you. But I was going to show you what's going on with some of the numbers here. So I'm going to put it on my math cam. And let's see if I can zoom in on it for you a little bit. If you look at this credit card, what I have is the beginning numbers identify that it's a Visa card and that they identify the bank that issued it. And then of course I have numbers in here that show my card number. But at the end, my last digit is a 2. The last digit of the credit card number is called a check digit. And the purpose for this is that when you, let's say you buy something on the internet, or maybe you read your credit card number over the phone to buy something, if you get your number a little bit wrong, if you type one of the digits wrong, or maybe you accidentally, put 2 of the digits in the wrong order, the computer will know that you have not entered a valid card number, and it knows this before it even calls the bank to see if you even have any money to spend. So how does it know? Well, there's a mathematical procedure done with the numbers. It was planned this way to catch little errors in case, like I said, you just typed the wrong number or something, which happens. So maybe this has happened to you. You've gone on the internet to buy something and it actually says, oh no, that's an invalid number. Well, it didn't check in with your bank yet to check that. It knows right off the bat that the number you entered is not valid for a credit card. So I'll show you how this works, and since I don't want to reveal my number to all of you, nothing personal, I'm sure you're all trustworthy, I've made up another card number. Now, I have no idea whose number this might be. It's not, I don't think it's a real number, but it's a valid number as far as our example will go. So if you have a credit card of your own, what I want you to do is write down the number just like I did. And I'm going to show you a little trick with the numbers and show you how a computer knows if this is a valid number or not. And the whole key is this last number, in my case it's a 1, has to be the right value to make it work. So here's what I want you to do. It doesn't matter how many digits you have. You're going to start at the right end, and as I mentioned, this first digit is a check digit. So not that one, but starting with the next one, going from right to left, I want you to underline every other number. So the first one that I will underline is actually the second to last one, and then just go right to left all the way down and outline or underline every other number. Now, what we're going to do next is you're going to double all the numbers that I outlined, and the ones that I didn't outline or underline, I'm going to leave the same. So, for example, the 4 I underlined is going to become an 8. Then the 4 next to it stays as a 4. The 1 will double to a 2. 7 will stay. The 5 will double to a 10. 4 will stay as a 4. 8, double it to 16. Keep the 6. Double the 1 to 2. Keep the 7. Next one's an 8, double that to 16, keep the 5. Next one's a 6, double that guy, 12, and I have a 4, double the 1 to make a 2, and lastly I keep the 1. Now what we're going to do is we're going to add up this new set of numbers, but there's a little tricky part I have to tell you about. When we doubled numbers and they became a 2-digit number, like for example, see this 16 right here? I don't want you to count that as a 16. I want you to count all these as single digits. So the 16 I'm going to count as a separate 1 and a 6. So then we're going to add up all these numbers. So I actually started with 16 numbers first. We're going to have a little more than 16 when we go because some of these 2-digit numbers we're going to count as separate numbers. So we're going to add all of these up, and the algorithm they call it, or the procedure is, the number has to end in 0 for a valid credit card number. So even though your credit card number is totally different than mine, at least I hope so, if you do the same procedure I'm doing, you'll have the same result. Your answer, when you add these up, will have to add up to a number ending in 0. Otherwise, it's an invalid credit card number. All right, so let's see if we can add these up here in my head. 8 and 4 make 12. 2 is 14. 7 is 21. Now, this is not 10. This is going to be 1 and a 0. So I had, what was it, 21 already, right? So it's going to be 22. Then add 0, I still have 22. 26. This is a 1 and a 6, so 27, 33, 39, 41, 49. This is a 1 and a 6, so 50, 56, 61, 62, 64, 68. Uh-oh, mine's not coming out right. I must have added wrong. You'd think I could add by now, huh? All right. I added this ahead of time to make sure it would come out right, so I don't know if I just did it wrong in my out loud in my head or what. But this total should come out to be exactly 70. it has to end in 0 or it's an invalid credit card number. So yours might not be 70, it might be 80, 90, or 50 or something, but it still has to be a number ending in 0. Otherwise, the computer knows to reject it and make you retype it in again. Then, of course, if it is valid, then it's going to check and see if you actually have a valid credit card account and if you have balance available and all that. But it tries to save time and check and see if it's even valid at the beginning. So I hope you check my arithmetic, since I just did it in my head and I did it wrong. It should come out to be 70 exactly. All right, there's another little trick with barcodes I'll show you a little later in the show if we have time. But I thought you might find that interesting, and it should work even for your credit card, no matter what kind of credit card it is.
Hey, Mathman Dan here. You know, photography is a little hobby of mine, so I was out here at Lake Henshaw taking some nature shots. And wouldn't you know it, there is some math involved. If you have a camera, a digital camera, there's lots of settings you can change, actually the old cameras as well. And this is an SLR, but also the little pocket cameras have the same things. Basically, a certain amount of light needs to hit the sensors in here, and there's two main ways to control that. One is the shutter speed, and the other is the aperture. So the shutter speed just means how long the shutter's going to stay open for light to hit the sensors. And you'll see numbers on here like 500 or 800, and all that means is that if you choose 500, it's going to open the shutter for 1/500th of a second. It's pretty fast. The aperture is a control of how big the lens opening actually gets. And I know you can't see it on your camera, but inside there's actually like a device that can open and close a circle just to let a certain amount of light in. And those have stranger numbers like 2.8 and 5.6. So what are those measuring? Well, it is a way to measure the opening, and it's all based on a ratio. Back at the studio, I will show you exactly how that works. But before I take some pictures, you might ask yourself, well, why do you need two different controls? Why does it matter? Because the truth is, there are lots of combinations that will let in the right amount of light. I can have a big opening and shut the light off really fast, or I can have a small opening and let lots of light in. But if you make the shutter move fast, you can capture fast-moving objects like animals. But if you do the opposite and you let a lot of light in with a large opening, then unfortunately it makes the range of focus very small, so your focus has to be extremely precise. So there's this trade-off. Do you want sharp focus in a narrow area, or do you want to be able to stop something in its tracks really fast? So back at the studio, I will show you a little bit about exactly how those f-stop numbers, they call them, show up. In the meantime, I got some pictures to take. See you in a minute.
All right, so here's the camera I was using, and I promised to follow up on some of those settings, how they work. So one of them I mentioned was just how long the shutter is open. That's pretty easy to understand. The other one's a little stranger. It's called f-stop, commonly refers to the aperture, and that's just a measure of how open the shutter is going to be, or the aperture inside rather. So there's a way to change the opening of how much light you're going to let in. And if you actually learn a little bit about photography and look at these numbers, they might seem a little strange. So I was going to show you where these actually come from. They are a simple ratio, as I mentioned. And on my computer here, I have a little formula written out. This is where these f-stop numbers actually come from. So it's simply a little fraction you make. It's the focal length divided by the aperture diameter. And I thought we'd do a simple little example here. So the focal length, by the way, that's the distance between the end of the lens and the digital sensor, or the film if it was a film camera. So basically that's an indication of what size lens you're buying. This happens to be a 200 millimeter lens. So I'm going to go ahead and put in there, we have a 200 millimeter lens. Let's see. Wait, hold on. I get my brush back. There we go. Hold on. If I can find it. All right, hold on. So we do a little example here, 200 millimeter lens, and then I'm going to make up an f-stop number. Let's just say, because I can actually set these. Let's just say I had it set to an 8. We could figure out what diameter that would match to, and that's really going to be the true opening on my camera of the aperture of how much light will come in. So we can do a little rearranging here, and you can figure out that D is going to be 25 millimeters. So if you were able to look inside my lens, you would actually see a 25 millimeter opening. So one thing to point out here is one reason the numbers may seem a little strange. Look at that fraction. If you make the aperture diameter larger, it's on the bottom of a fraction. That's going to make the f-stop number smaller. So it's sort of inverse what you might think. A larger f-stop number is actually a smaller opening or less light. So I actually brought with me an older lens, a smaller lens, that I can show you the inside mechanism of how this actually works. So over here on my math cam, this is an older lens from an old film camera. And what I can do, so I can get this just right for you. What I'm going to do is, you can see a little opening there in the middle. I'm going to actually do what the camera does. I'm going to move this, and you can see the opening get larger. And this is as wide as it will go, but you can actually, when you make a setting, your camera switches to what you want here. Now, one more thing I'm going to show you on this old lens, there's some numbers on here, and these are actually the f-stop numbers. These at 22, 16, 11. The newer lenses don't print them here because it's all electronic, so it does it internally, but the old ones, you actually had to turn a dial and set these. So what I want you to notice, and I'll explain this in a minute, is look at these numbers. They're kind of strange. It starts with a 1.7, 2.8, 4, 5.6, 8, 11. Why that list of numbers? And they seem almost random. What's the story with those? So I'll explain that in just a second. All right, so back to my computer here for a second. One thing I wanted to show you was why would you use different f-stops? I mean, what does it really do for you? And I mentioned it lets more or less light in. Well, the truth is your camera exposure needs a certain amount of light to get the picture. And you can always get that amount of light, but you're doing it as a combination. You open it up, the lens, a certain amount, and let a certain amount of light in, and then you have to open the shutter for a certain amount of time to let the total light in. And you can raise one and lower the other and get the same total amount of light. So the question is, why would you change those? And one thing I mentioned when we were out taking pictures was, if you have a slow speed of shutter opening, you can't capture something that's moving fast. You'll see a big blur. I'm going to show you what happens if you change the f-stop though. So I brought in a couple pictures I actually took myself. It's just a simple picture of a watering can, and the background is a chair. What I want you to notice is, I took two pictures. There's the first one, and here's the second one. Now watch the chair. The watering can looks almost exactly the same, but watch the difference that happens with the chair. So one, it's fairly blurry, and one, it's a lot clearer. This blurry one was an f-stop of 5.6. That's a little on the low side. I mean, a lot of lenses go a lot lower. But what that does is it makes a shallow depth of field, and that means that the part away from you that's going to be in focus is small. So I have the watering can in focus, but not the chair behind it. The advantage to this is it's letting a lot of light in. So in this example, my shutter was 1/125th of a second. That's pretty fast. Not fast enough to stop, running animal, but it's going to do pretty good. The other one, the chair is much clearer. This was an f-stop of 16. So a lot more than the original one. The chair's not perfectly in focus, but it's much better. But I had to leave the shutter open for a 15th of a second. And that might sound like a short time to you, but a 15th of a second is not even good enough to counter for your unsteady hands. Generally, you need a 60th of a second to even do that. So anything you took with this setting, if it weren't sitting on a tripod, would come out blurry. So there's all these trade-offs you do, and sometimes photographers do them for effect. They want the background blurry or not, and this is where the f-stop comes in. So one last thing I was going to show you about this, because I thought it was interesting. Why are these numbers the numbers that you see on a lens? And even if it's electronic, you'll still see the options listed for you. So we're going to go back to my little computation here, and I listed the numbers off that lens. If you can see them on the left-hand side there, these are the f-stops on that lens I showed you a second ago. 2.84, 5.6, 8, 11, 16, 22. They do not increase by the same amount. They almost seem kind of random. Well, the truth is they are not random. They are linked to how much light is coming in, and they're roughly doubling the amount of light each time. But you have to think about this. Light is based, when it's coming in a circular area, it's based on the area, not on the diameter. So what I've done is I've gone ahead and computed the diameter of the aperture for each of those f-stops for that little lens I showed you, and then I computed the area. And one thing we can point out here is the areas are roughly going in half each time down the list. So I have a 250 first, then it goes to 123 area. That's roughly a half. Not exactly, but roughly. Take it in half again, we got 62.6, that's about right. Keep going in half again and again and again, and you're getting down the list. So those f-stop numbers are set up on purpose, so they will half or double the light depending on which way you change them. And that means, you guys remember a formula for area of a circle, right? Pi r squared. So the area is linked to the square of the radius. So if you play with the radius or the diameter, it's actually the square of that affects the area, and that's how much light is coming in. So if you go back and look at my f-stop numbers, if you were trying to figure out how do you get from 2.8 to 4 and 4 to 5.6 and 5.6 to 8, you're roughly multiplying by root 2 to do that. Because think about that, if you double the diameter or the radius, you would actually make the area 4 times bigger. So you take the square root, that's how much you multiply it by, and that makes, if you square that, you get 2, and then it doubles the light. All right, so if you are out taking pictures, even with a little camera like these little pocket ones, which take very good pictures, by the way, this one you can't actually set those things yourself. This does it all automatically. But I'll tell you, the camera itself is setting these things. It is doing the shutter, and it is doing the f-stop. And in fact, if you put the pictures on your computer, you can actually have a lot of software will actually show you what those settings were. So even though you couldn't change it, you can see why this picture was blurry or this one was clearer, and it's all linked to those different values. All right, next time you're taking pictures, you have a little more to think about, right? Now, I mentioned a little earlier in the program that I showed you a trick for your credit card numbers, and I mentioned that there's a similar trick for what are called UPC codes. So if you have any product in your house, I mean, literally just about anything you could buy from a store, if you notice when you go to the checkout counter, they scan the barcodes. Well, I brought a DVD with me. This is Finding Nemo, and if you look on the back, there's one of those barcodes that they use to scan at the cash register. Well, have you ever been at the cash register and for some reason it won't scan? You know, I don't know, maybe the barcode's a little messed up or their scanner's a little dirty or something, and they actually go in and type it in by hand? Well, these have a similar trick with the numbers, so that if the person types them in a little bit wrong, for example, if they get one digit wrong by 1, or if they maybe accidentally put 2 digits backwards, it'll know. It won't just come and say it has the wrong product. It'll say, oh, that's not a valid number, you got to enter it in again. So this is important because otherwise, if you just put in a wrong number and it might, you know, you bought a Finding Nemo DVD and they charge you for some, you know, mattress that costs $800 or something, you'd be a little upset. So the idea is, how can they catch a mistake without knowing that what product you're actually buying? So here's how it works. Now I'm going to show you this on my math cam here, the code, and we're going to write down the number. See if I can zoom in on that a little bit. See if you can see that nice and big. Okay. So the number I have, there's 12 digits in this number, and if you look, there's little tiny numbers off to the sides here. So my fingers look big, huh? Okay, so here's the numbers. This is the code, and these little numbers on the edges, those are part of the code as well. So I'm going to write that code down, and I'm going to show you a little trick for how the computers know if you typed it in wrong or not. So the number I've got here, I'm going to write a little bigger because it's so small there. It's 7, 8, 6, 9. And you know what, if you want to try this with another product in your house, just grab anything and you can do the same trick I'm going to show you. 7, 8, 6, 9, 3, 6, 2, 1, 5, 5, 9, 5. Okay, so I'm going to zoom this guy back out. I'll put the number here and I'll show you a little trick we can do with it. So the way this one works, this one's a little different. What you're going to do is you're going to start at the first number, and I want you to underline every other number. So when you get to the end, the 5 will not be underlined. You should have the 5 as the 9 should be the last one underlined. So underline the 7, the 6, the 3, go every other number. Now the last digit, the 5, is a check digit. This is just like the credit card. So in other words, this whole number is identifying the product, but this 5 at the end is serving only as a way for the computer to know if you made an error. So the trick is, take all these numbers that I underlined here, and I want you to multiply all of them by 3. And then we're going to add up the new set of numbers. So the underlined ones multiply by 3, and the other numbers keep as they are. And you can try this with any product in your house that has a UPC barcode. By the way, that stands for Universal Product Code. It was actually invented quite a while ago. It was pretty smart the way they did it. They made it so you could scan things. It doesn't matter if it's upside down or what. The scanner can figure out what the number is. All right, so take all these numbers, multiply them by 3. So this first one will be 21, and we're going to add all these up. So the 8 stays as an 8. The 6, I'm going to triple that to 18. The 9 stays a 9. Triple that 3 I underlined to a 9, then we have a 6. Triple the 2 to a 6, then we have a 1. Okay, triple that 5 to a 15, then we have a 5. And finally, I have tripling that 9 to a 27, and then the check digit at the end. This total, again, the same deal, has to come out to end in 0. If it doesn't, then the computer knows you made a mistake. And if you got one of these numbers off, or you actually switched two of the numbers, it won't come out to be 0. So chances are the computer's going to catch it for you. So maybe I shouldn't risk adding these up in my head again, so I did it beforehand. This comes out to be exactly 130. So the guarantee was it has to end in a 0 to be a valid UPC code. So you know what, try stuff around your house. You'll find all kinds of things with these little barcodes on them. I have CNN up on my computer here. They're, of course, announcing that the House of Representatives is now Democratic. The Senate, last I checked, just before the program, still had 1 seat undecided. It was 50 seats for the Democrats and 49 for the Republicans. So we're not sure if it's a tie yet or if it's actually going to be a win for the Democrats. But I brought my magic 8 ball with me today. So the question is, will the Senate go to the Democrats. And it says, don't count on it. All right, you heard it here first. See how accurate that thing is. It served me well in the past, I must say. So if you've been watching the elections, number one, over the past couple months, actually, you've probably seen some political polls that try and predict what's going to happen. And even if you were watching yesterday during the election day, you probably will notice that they start calling certain elections long before they get all the results in. In fact, they're not going to have the official tallied results for a while, but they call the elections much earlier than that. So believe it or not, there's some mathematical basis to this. It's not just them guessing. And if there's a wide margin in the votes, it's usually easy to say, okay, we know where this one's going. But if they're close, it gets a little trickier. And in the recent past, some news stations got in trouble because they called it the wrong way too early. They were a little overzealous in getting the result out before the competition, and they blew it. So I was going to show you a little bit of the mathematical content in there behind the polls, because there's some information you probably see you have no idea what it means. And we'll see how it affects what you see on the television when you actually watch the elections. So with the polls anyway, what you'll usually see is they're going to interview a bunch of people or survey a bunch of people, and they're going to try and predict the future from those results. So there's two issues. One, they have to make sure that this is actually a non-biased survey, and that's harder than you think, because if you just call up 1,000 random people and ask them who they're going to vote for, you have to decide, am I really getting random people? If you call all people that tend to be more Democrats, for example, then you might have a biased result. So they try and be unbiased, but even if you do a phone survey, you're still getting the people who are willing to answer the phone from a number they don't recognize, for instance, or the people who are actually home, so maybe the people who don't work as much as others, or who knows what. It's very difficult to get an unbiased survey. But if you succeed in getting an unbiased survey, then there's a mathematical component to it. So for instance, I have on my computer here, I just found a copy of an official CNN poll. And if you read the language, it says that they interviewed 934 registered voters, but it also says that there's a plus or minus 3 percentage point margin of error. So I see this all the time. And what is a margin of error? If you're just thinking about it casually, you'd probably just assume that, well, they're telling me the result, and really it's plus or minus 3 percentage points that they could be off. You know what? That's not quite what it means. And actually, it can be misleading, and I've actually seen news stations use it in a misleading way. So if you take a statistics course, you'll learn all the gory details about exactly what this means. But we're going to give you the quick layman's version, okay? So I have another race here. There's actually a local race. We have Brian Bilbray running for Congress in San Diego County. And this was a survey published in a local newspaper. This was published just last Saturday, and it's talking about how they're predicting Bilbray would win, and it actually gives a percentage. So I'll show you what they published here. They had published that they predict 55%, and they got that by surveying 550 people, and they claim a plus or minus margin of error of 4.2%. So we're going to figure out what exactly that means, and we'll see, of course, how close they were. It turns out they were actually pretty close, but I have the results on my math cam here. This is what the survey claimed. They said 55%, they polled 550 people, and the margin of error is 4.2%. So what this means, this margin of error, it's not, I don't know, it's not quite what you might guess, in the sense that this doesn't guarantee for sure that Brian Bilbray's result will be within 4.2% of 55%. In fact, every time they do a survey like this, they're supposed to publish a level of confidence, and that's always implied, and they often don't. So technically speaking, this margin of error means nothing if you don't know what level of confidence it was determined at. But normally what happens is they use a 95%. I'll show you what this means. Let's assume a 95% confidence level. So what specifically this would mean is that we're going to take 55% as our observed total. This is our observed result of the election, and we're going to go plus 4.2 percentage points on that to the high end. That would be 59.2. And we're going to subtract 4.2 to go to the low end. So that would be 50.8. So the way this works, this is the actual meaning of this margin of error. It means that there's a 95% chance that their survey within this range is enclosing the true vote total. So do we know for sure that the vote total is in here? No. We have a 95% confidence level. And what you can interpret that as is if this company or this newspaper did the same survey 100 times, 95 of those times, the interval you get like this would contain the actual result, and 5 of those times it wouldn't. So they only did one survey. Is this one of the 95 that has it, or is this one of the 5 that doesn't? There's no way to know. So you can't take this as law. They don't know. The mathematical results behind it, though, says you have a 95% confidence that the real result is within these boundaries. And it turns out it was. I wrote it down here. The actual result was 53.3, so it was definitely within these boundaries. So that makes their survey seem sound. Now, there's a couple interesting things about how they figure out this margin of error. For example, how did they get it? Well, there is a little formula I'm going to give you, and you can get much more sophisticated with it if you like. But the formula they use is for a 95% confidence level, it's 0.98 divided by the square root of the number of people in the survey. So there's a couple interesting observations here. And the main one is that you might find surprising is the margin of error has nothing to do with this total size of the voting population. So it doesn't matter. I mean, they surveyed 550 people. It doesn't matter if you do this for a county of 10,000 or a whole country of 100 or 10 million, let's say. The results would be the same. And the mathematical theory behind this is that if there is a true average for the population, then the more people you pick, the closer you will get to the real thing. And mathematically speaking, if you really choose randomly, it's just as determined by the number of people you start getting the answers from as far as how close you're going to get to the actual answer. So you don't have to have a certain percentage of the overall population. It really is related to simply how many people you actually talk to. And the statistical link to this, if you care in the future to get more detailed about it, is it's related to what's called a normal distribution, which is basically a bell curve. And you've probably heard that phrase before. The idea is that if you start choosing randomly from the population, their results will start forming a bell curve around the real answer. And that's how come I can't tell you what the real answer is, but I can tell you that within these boundaries, you have a 95% chance of actually having the real answer in there. So if you want to do a quick calculation, you can see that this is actually what the newspaper did. They 0.98 divided by, they interviewed 550 people. If you do this computation, hold on, I'm going to do it on my calculator here. We should see the same number they have if there's things are working with us. It says 0.0417. That's 0.042 rounded. So that is 4.2%, exactly what they claimed. So this is how it works. So next time you see margin of error, this is what they actually mean. They're giving you a 95% level of confidence of where the real answer might lie. So sometimes I've seen people read more into this than they should. So for example, I've seen reports where, I don't know, one candidate had 52% of the vote according to their survey, and one had 48, but the margin of error was 4%. So they'd say, look, there's overlap, so really these surveys tell us nothing. They could be perfectly tied. That's not really accurate. If one's getting 52 in the survey and one's getting 48, odds are, I mean, you can kind of have a similar confidence level that the one ahead is actually ahead in the polls. So it's not, you can't use it literally to say it could be anywhere in that span. It's a statistical measurement, a probability, if you will. It's most likely to be in the middle of that span, but 95% can be somewhere in there. So anyway, if we have a few minutes later, I'll show you a couple more little tidbits about how this stuff works. But maybe you'll know a little more now next time you see a poll on TV or in a magazine. You see a little margin of error, and you can actually figure out what exactly that means, because they don't really tell you, and they probably should.